Now that we've discussed, how to calculate phase diagrams for vapor-liquid equilibrium phase diagrams involving ideal solutions, what we're going to do now is we're going to add a layer of complexity, and now we're going to start looking at mixtures in which the vapor phase is still an ideal gas mixture, but now the liquid phase is going to be a non-ideal solution. Okay? And even though it's a more complicated system, mathematically there's only really one change that we need to make. And that's when we define our pressure equation for each of the partial pressures, rather than just using the regular version of Raoult's law, we're going to use the modified version of Raoult's law, where now we have the activity coefficient in there. Okay. All right. For the vapor pressures, it's still the same. You would still use Antoine's equation. And the vapor mole fraction is also almost the same, except once again you would use that modified form of Raoult's law that has the activity coefficient in there. And so calculating the pxy diagram or the txy diagram would basically follow the same steps, but now there's an additional calculation you need to make, which is now you need to calculate for those activity coefficients. And the value of your activity coefficient is going to depend on whatever you use for your model for the excess Gibbs energy. Okay? And so this is where you would need to consider if you're going to use a Margulies equation or the Van Laar equation or etc. Okay? All right? And so, conceptually it's just a very simple change. But the fact that we're adding in this activity coefficient, which has its own complex relationship with temperature and pressure, adding in these activity coefficients can greatly change the phase diagram. Okay? And so it could cause it to deviate greatly from the ideal solution versions.